sports field. There is now a statue there, and it's a bizarre hunk of metal which is carved by some artist who made it look like a tortured man, or if you turn, a mushroom cloud. Very bizarre looking thing. How do you make a nuclear reactor? So the problem is not very difficult. It's similar to this. You just don't want it to blow up. So you just take the two pieces and you get them close enough to each other so that they start to react, and then you don't let them get any closer. The problem with that is that it's real sensitive. If you get them a little too close, they blow up. They melt. So you have to have some way to control them. Now, it turns out there's a really easy way to do this. You get some uranium and you construct it into rods. These rods have little fuel pellets inside them, just chunks of uranium. There's not a lot of uranium in here, and it's not very enriched. You can't turn it into a bomb. It's like 20% enriched, so it just can't blow up. Neutrons will come off of these things. They fission every once in a while. The uranium atoms fission, neutrons come off, but as they come off, they tend to come off at an angle that doesn't send them down the length of the rod. So there's very little chance that one of those neutrons will actually interact with another uranium atom in the rod. Real low chance. And there's another thing about these neutrons. They're fast. They're coming out with high energy. And high energy neutrons don't like to react. So they can pass through an awful lot of uranium without reacting. If you slow them down, then they're much more likely to react. So what we do is we get several of these rods, and then we put something between them that slows the neutrons down. Water will do. So we put water on top of the rods. Now, Enrico Fermi did not use water. He used graphite, carbon, which will also slow the neutrons down. Works fine. Whatever you use to slow the neutron down, it's called a moderator. It moderates the neutrons. So the neutrons pass through the water, they get slowed down, they interact with the next fuel rod over, and they cause it to fission. But then when it fissions, it sends neutrons in many different directions. It passes through the moderator, and it causes one of the other fuel rods to fission. So the fissioning happens between the rods, not inside the rod, which is interesting. Now, you can also put material in here, other rods that you can lower. They use cadmium for this. It doesn't matter what you use as long as the nucleus of that atom likes to absorb neutrons. There are several atoms that have stable isotopes with 1, 2, 3, 4, 5, 6 more neutrons in them. So you just stick some atom in there that's perfectly happy to swallow a neutron. And then if you do that, these rods will eat up the neutrons and prevent any kind of reaction from occurring. So you got two things going on. You got the moderation effect, which increases the reactivity. You've got the control rods coming down, which can decrease it. Now, in a water-based reactor like this one, what happens if, something goes wrong? And they let it get too hot. Well, then the water starts to boil. Water boils. The water level starts to go down, the moderator goes away, the reaction shuts down. These reactors are inherently safe. They cannot run away. They cannot suddenly go balooey. They've got a negative feedback loop built into them that shuts them down, and it's a passive feedback loop. You boil that water away, there's not going to be any reaction. That doesn't mean that it's safe. Because these rods have lots of gunk in them by this time. There's a whole bunch of dirty, icky stuff in there, fission products, and they're going to continue to fission by themselves. There's strontium and cobalt and all kinds of horrible stuff. So the rods generate heat all by themselves. Not a lot. Enough to melt them. Not enough to power the reactor. But there's enough heat created by the rods to melt them. So even if the water all boils away, although the reaction has shut down, the rods can still melt, fall to the bottom of the floor. The reactor's toast at that point. Kind of happened to 3 Mile Island. Not quite, but close. It's not a China syndrome. Anybody remember that stupid story? Mm-hmm. Right? The uranium will melt and go to the bottom and continue to react. No, it doesn't. It shuts down. The reaction shuts down. You can't have this pool of uranium at the bottom reacting with itself because there's no moderator. Okay. What if you use graphite in here? It works just fine. Moderates the reaction perfectly, but if the graphite catches fire, it moderates even better. There's a positive feedback loop built into that one, and lots of graphite reactors were built in the past, and there were lots of safety measures. And you could put cadmium rods in there to slow the reaction down. You could even put water in there to try and help slow the reaction down, but graphite has this tendency to accelerate the reaction if it starts on fire. And something like that happened at Chernobyl. Chernobyl was a graphite reactor, or a partially graphite reactor. And it caught fire. And the reason it caught fire is because a bunch of guys turned off the safeties. Some physicist, high political guy wanted to do an experiment, came in at third shift, said, I want to run my experiment. The safeties kept on tripping. He said, well, turn that one off. Another one tripped, turn that one off. Another one tripped, turn that one off. Thing caught fire. It's not rocket science to figure that out, but I guess if you're a nuclear physicist, you don't think about things like that. Fun, Chernobyl was a bad experience. Did you have to kill all your sheep? I was in England at the time. I was living in England at the time when Chernobyl blew up, and the English had to kill all their sheep because the fallout cloud passed over, and nobody wanted to eat the sheep. Now, I really doubt there was much radioactive, but still, kill all the sheep. Nobody could eat sheep for a while. Anybody been to Chernobyl lately? You can go there if you want to. It's a little bit of a tourist thing now. You have to wear a dosimeter. I haven't been there. I've just heard. You have to wear a dosimeter. There are places where it's safe to walk. There are other places with signs that say don't go here, and it would be a good idea if you did not go there. But other than that, it's there. It's people are there, animals are there. It did not turn into the Holocaust of horror that people thought it would. We as a society have managed to convince ourselves that anything nuclear is deeply evil and troubling, and we're terribly afraid of it, and that unfortunately hampers our ability to make progress. We should be cautious, we should be careful, we should not be stupidly afraid. By the way, I'm not talking about, well, I guess I am. So, architecture.
Back to the real life.
You call this real life? I call that real life.
No, because it's the work of those. It's thoughts of those. I'm not thinking those thoughts. I'm thinking those.
Well, good. That's good. My son came to me several years ago with an application. And I looked at it, and I noticed something about this application. It looked like this. It had a directory in it for models and views and controllers. Now, that made me think, why does it have those directories? And so I went back and found an old application that I had written about 6 years ago. And this is it. And what did I find? I found models, views, and controllers. Now, I had written this because I was teaching myself Rails. I wanted to learn Ruby on Rails. And so I followed the book, and I did what the book told me, because that's what you do, right? And this is where I ended up. And I realized something when I looked at this application 6 years later, is that that application tells me that it's using Rails. It does not tell me what the application does. And that bothers me. At the highest level of this system, nothing tells me what it does, but it's very clear it's a Rails system. Yes, sir?
You can determine a Java application only when you see there's a source folder or a source Java folder that is what this application does. So you have to look at the names of the controllers or the models.
Well, I could look in there at the names of the controllers or the models. But why do I have to go that deep?
In Java you have to go that deep too.
Do you? Yes, you do, in Java. Because in Java you'll have similar kinds of folders, won't you? You have a view folder, probably, controller folder, maybe a models folder, I don't know. Do you have that? You got Spring people, you know? What it look like? Well, that bothers me. Why should the top-level structure of the application tell me that it's a web app? Now, the web...
Probably because it could be done by different people.
Fine, but the question remains, why should the top level of the application tell me that it's a web app? Why should the top level of the application tell me what framework is being used? Why doesn't the top level tell me what the application does? So I thought about this for a while, and I thought, well, that's strange, because the web is an I/O channel. It is not an architecturally significant element. It's an I/O device. And why would the architecture of the system tell me what I/O device is being used? We learned a long time ago that I/O devices should be independent. So it occurred to me that the web is just a delivery mechanism. It's a detail. Something that ought to be suppressed by the architecture, not amplified by the architecture. We don't want the architecture of our applications to tell us this is a web app. We want it to hide that information. I started looking at the architecture of buildings. This is the architecture of a library. This is the floor plan of a library. And notice what it does not tell you. It does not tell you bricks, wood, nails. It tells you nothing about the tools being used, nothing about the materials being used, at least not at this level. It does tell you what the building is for. Because you can look at it and you can see, oh, look, there's bookshelves, there's tables, there's desks here for check-in and check-out. This is a library. The architecture tells you what the building is for. And if you want a better example of that, that's a church. It's obviously a church. Oh, it might be a theater, I suppose, but no, it's a church. I mean, you can pretty much tell. There's an altar there, a bunch of pews, a little area there, classrooms for the Sunday schoolers. The architecture of these buildings tells us the intent of the buildings. And that made it clear to me that architecture is about intent, not about frameworks, not about I/O channels. Now, it turns out that this is an old idea, an idea that we had in the 90s, and we lost it. We lost it because of the web. Anybody remember, the craziness going on in 1999? We were all going to be trillionaires. We were all going to take over the world, the web with Java, the Oracle, blah, blah, blah. We were all going to just, And companies were hiring programmers in droves. If you had a J in your name, you could get hired as a Java programmer. You didn't have to know Java. Just tell people you knew Java. That was enough, because we didn't have enough programmers. We'd hire anybody. Nowadays, you can do that in the United States if you've got an R in your name. Yeah, watch out for the collapse of the social networking bubble. So we got this horde of programmers in lots of code getting slammed around left and right. It's all about the web. The web is everything. Yay, hooray for the web. And then, of course, the bubble collapses, and got a bunch of guys wandering around wondering what the hell happened. And they're carrying signs saying, "We'll code for food." Come out of the back end of that. And now we're struggling to build up these systems. A load of very young programmers who really didn't know what they were doing. They're still writing gobs and gobs of code, no clue about what architecture was. And all of this lovely stuff that we had learned in the 90s was lost. But here it is. This is the guy. His name is Ivar Jakobsen. Some of you know this name. He was one of the three amigos who helped Grady Booch and whoever that other guy's name was, I can't remember now, come up with UML and the unified process and all of this stuff. And we look back on that nowadays and we think, wow, they were not really on the right track with all that stuff. Jakobsen had written a book several years before. This is the book. Object-Oriented Software Engineering, a use case-driven approach. And this may strike a nasty chord with you. Anybody remember use cases? Okay. And the world went crazy over use cases during the dot-com bubble. But they went crazy because they were searching for the perfect form. And there were people making lots of money designing forms for use cases. It's got to have a name. It's got to have preconditions and postconditions and actors and unactors and secondary actors and all this crap. He never said anything like that. To Jakobsen, a use case was a very simple document. It looked like this. A use case is a description of a business rule. It has inputs like this. For example, create order. Got some inputs. These angle brackets I stuck in there. They're not part of Jakobsen's syntax. I just stuck them in there. The data coming in is the customer ID, the shipment destination, payment information, whole bunch of data. Notice that it doesn't tell you where the data came from. It doesn't tell you that it came from a form on the web. Doesn't tell you whether it came from text boxes in a thick client or even a punch card. You just don't know where it came from. Then he describes the primary course. Order clerk issues create order command with the above data. That's actually not even part of the use case. That just triggers the use case. System validates all the data. Doesn't say how. It validates. System creates a new order and determines the order ID. Doesn't say how, but got to have that new order ID. System delivers the order ID to the clerk. Doesn't say how. Just very simple, easy to understand statements. At the bottom, you have some exceptional courses. What if something goes wrong? Validation error. Well, then deliver an error message to the clerk. Nowhere in here does it say web. Nowhere in here does it even hint about the I/O channels. It's just the business rule. A raw, unadulterated business rule. And we can put it into an object. Because that's codable, that business rule. You've got a bunch of input, you got some rules to apply, it generates output. It's codable. So we could put it into an object. Now, he called the object a controller. I don't want to use that word because it's too much like model view controller. So I call it an interactor. Maybe a better name would be use case. It's just an object. It's an object that takes data in, processes the data.
Sorry.
No problem. Processes the data and puts output out. The interactor contains application-specific business rules. Business rules that have only to do with the application. Now, let me explain that. Some business rules apply to many applications. For example, let's say you had a business rule for calculating the total of an order. You might use that business rule in an order entry system. You might also use that rule in an order processing system. The same rule. So that is an application-independent business rule. On the other hand, an application-specific business rule is a rule that only applies to this application. And that's what all these interactors are. All the use cases are specific. Where do we put the application-independent business rules? Well, they go into other objects, which Jakobson called entities. Nowadays, we would call these business objects or domain objects. The entities or the domain objects contain the application-independent business rules. So now we have this interesting pair. The interactor, the use case code, talks to the entities, and usually there'd be more than one, right? There might be an order entry, a line item entity, a customer entity. The interactor would be talking to those. And then Jakobson described a third kind of object. He called it a boundary object, or he actually called it an interface object at first, and then later turned it into a boundary, not to be confused with a Java-style interface. They are, however, Java-style interfaces. Boundaries allow data in and out of the interactor. So here you see an interactor which uses one boundary, that is the output boundary, and it derives from another boundary, that is the input boundary. So the interactor derives from functions here which supply input to the interactor. It calls other functions here which provide output from the interactor. So you see both I/O directions that way. Although notice that the arrows are all pointing in the same direction. That's the key to this particular issue. Whether it's input or output, it doesn't matter. All the arrows point away from the interactor. We can see how this works. We've got a user down here. User uses the delivery mechanism. Let's say it's the web. Doesn't have to be. Could be anything else. The user does something, I don't know what, enters data into a form, pushes submit, something like that. And the delivery mechanism creates a data structure called the request model. This data structure contains all the data that the user specified. This should not be confused with an HTTP request, although it has the same data in it. This does not know about the web, does not derive from anything web-related. None of the fields in here are web-related. They have all been unpacked and turned into raw data. So this is a raw data structure containing all of the data for the use case. It gets passed into the input boundary, which the interactor derives from. So the interactor gets it right away. And the interactor reads it, figures out what to do, talks to all the entities, telling them what to do. Then it turns around, pulls data out of the entities in order to construct a result model. A result model is another raw data structure. No trappings of the web, no knowledge of the web. Just a dumb data structure that then gets passed through the output boundary to the user. The delivery mechanism probably formats it somehow. What we've got there is this really interesting boundary right there. And this over here is the web. Notice that the web has arrows pointing inwards. Nothing over here knows about the web. Has no clue. All it knows about is that these data structures that come in, and there's data structures that go out. Could you test these interactors? Huh? You create the input data structure, you hand it to the interactor, you get the output data structure, you check it. Do you have to have the web server running to do that? Nope. The web server doesn't have to be there to check this. You could check the entire function of your system, all the business rules, all the use cases, tested without the web server even turned on, without the web server running. The web's not part of it. So then what's Model View Controller for? Isn't Model View Controller the thing that's supposed to be doing this? Right? Controllers take the URLs, they control the dance of the business objects, they gather all the data from the business objects, pass it all into the views. This guy's name is Trygve Renskog. I didn't say it correctly, but you can't understand it because my voice is crazy. Anyway, Trygve Renskog is the guy who invented Model View Controller in 1970-something. He was a Smalltalk programmer. This was a Smalltalk design pattern. I met him last year, first time. I was in a speaker's lounge at a conference in Norway, and in walks Trygve Renskog. That's Trygve Renskog. And you know, I'm sitting it there. I'm looking for a place to plug in my laptop, but you know, there's Trygve Renskog over there, so I'm kind of walking around like this, and he sees what I'm doing, and he reaches down and he hands me a power strip. And you know, I took the power strip and my hand brushed his. I haven't washed that hand. And even I have my heroes. And this is one of them. Trygve designed this scheme called Model View Controller. And it's a fascinating idea. The model is a purely mathematical model of whatever it is you're trying to represent, a set of business rules, if you wish. The view is a way to represent the model on some I/O device, some O device, some output. And the relationship between the view and the model is an observer pattern. This is a callback mechanism. The model doesn't know about the view. The view knows about the model. The controller looks at input, particularly keystrokes and mouse clicks, and gives directives to the model. This was meant to be used at the size of a button, or a checkbox, or a circle, or a square, a text field maybe. It was not meant to be used to represent.
Hi, I got something for you.
Oh, thank you.
Yeah.
Come in.
You just
Put it.
on the table.
Yes, it's for me.
Yeah, for everybody.
Oh. It's for me. It was not meant to be used at the level of a page or a screen. It was little tiny Model View Controller triplets. If you had a page of stuff, you had lots of little Model View controllers all over the place. We have completely screwed this up. Right? Nowadays, Model View Controller doesn't look like this at all. Nowadays, Model View Controller looks like this. You've got the web out here, and by some crazy magic, the web figures out which controller to invoke. And it hands the controller this horrible hash table or something of parameters and blobs and stuff, which the controller then takes apart and then reaches into the business objects and starts to mess around with them. So all the controllers know about all the business objects. And then the controller finally says, well, I'm done with that, and hands the control over to the view, and now the view has to go back to the business objects and say, okay, give me all that stuff that he did, and you do, and I'll format it and ship it out. So all the view files know about the business objects, all the controllers know about the business objects, the big tangled mess. Rule number 1. The view should not know about your business objects. You don't want the view knowing that stuff. The view is just an output device. And what you'd like to give the view is some very simple little data structure. Some of you are doing MVVM in Microsoft world. This is a good idea, one of the few to come out of Microsoft, but it's a good idea. This notion of a view model is a powerful idea. In the Java world, what we see instead are JSPs or some other thing that reaches deep into the business model space and tries to extract data. And the problem with all of that is that these objects get polluted with view-like methods and controller-like methods. The controllers need services, and so they put those services in the business object. The views need services, so they put those services in the business object. And the business objects suddenly have methods in them that know how to format the elements for the view. Nasty stuff. The way we want this to work is like so. At the end of an interaction, at the end of a use case, the response model is created by the interactor. This is a raw data structure. It doesn't know that it's part of the web. You could output this on a console if you wanted. You could output it at a thick client. You could output it on the web. You could output it over a service-oriented architecture. I don't care. It's just the data. Thank you, Angela. You're staying.
I just want to have a feedback sheet.
Yes, feedback sheet. I haven't filled them out yet.
No, I you can.
Yeah, I will, yeah. Okay, so you have to fill these out. I don't. You have to fill these out. The interactor passes the response model out through the boundary, the output
Machen wir nachher in der Pause.
The thing that implements the output boundary is called a presenter. Microsoft people are familiar with this. Java people, some of you are familiar with this. This is called the model view presenter pattern. The job of the presenter is to take the data in the response model and convert it into a view model. Now, I don't want the interactor doing that because I don't want the interactor knowing how it's viewed. The presenter lives on the other side of the boundary, on the other side of that black line. It knows how to take that data structure and turn it into this data structure. What is this data structure? It's a bunch of strings. That's what gets displayed on the web, right? Bunch of strings. This is the bunch of strings that gets displayed on the web. All of the formatting has been done. If there are dates, they've been formatted. If there's amounts, they've been formatted. If you've got to put parentheses around negative numbers, the parentheses have been stuck in. If there are menu items that need to be grayed out, there are booleans in here that gray them out. If there are buttons that have names, the names are in here. If the buttons need to be grayed out, there are booleans in here that gray them out. Anything that gets displayed, the data for that display is up here. And then the view is stupid. It's so stupid. All it does is go to the model and say, okay, take that, put it here, take that, put it there, take that, put it there. There's no logic in there. You might find a loop in the view if there were some kind of looping structure in here, some kind of table. But other than that, you're not going to find much interesting stuff in the view. Because of that, I don't test views. There's not much to test here. And you want to keep it that way. You don't want to have a lot to test here. We'll talk about JavaScript later. That's not what I'm talking about here. This is just the output side of things. Don't want to confuse input and output with behavior. JavaScript is all about behavior. We'll talk about that later. Can you test the presenter? Well, yeah. It's an input data structure and an output data structure. Do you need the web server running to detect the presenter? No. Can you test the view? Yeah, if you want to, you can test the view. Because all it's doing is translating the view model data structure into another data structure called HTML. And you can check the HTML if you want to. I'm not, I usually don't. At some point, your eyes become the test. And at the view level, the kind of stuff I do with views is this fiddly stuff. Move this here, change that. It's all about your eyes. So I usually don't test this with automated code. But you could if you wanted to. If you wanted to test the view automatically, would you have to have the web server running? Well, you shouldn't have to have the web server running. Unfortunately, a lot of the Java systems have this weird dependency. They can't run the JSP compiler properly unless you've got the web server. It's a stupid system. I did, in fact, one time figure out how to invoke the JSP compiler without the web server running. It was a horror scene. It probably doesn't work anymore. Yeah, it worked once for me. This is the mode of operation I like. This heavy dark line separates the application from the web. And all of the dependencies cross it going in one direction. Architecture is often the art of making sure your arrows go in the right direction. Because of this, I can now separate my business rules and have an architecture based on these interactors. At the top level of this part of my code, I have interactors. Those interactors have names: create order, delete order, process order. They're all the use cases. I can see that architecture at the top level. And there is no dependency at all on this stuff. So the web is not even in there. Look at the direction of those arrows. The web is a plugin to the application. Remember we were talking about plugins earlier. The web is a plugin to the application. I could put this into a jar file. I could put this into a jar file. And I could deploy them independently. I could deploy the application. I could deploy the web. If I didn't like the web, I could make another jar file, a console jar file. And I could deploy the system with a console interface. If I didn't like that, I could deploy it with an SOA interface without changing the application. That's why we have jar files. That's kind of the picture without the entities off to the side. Interactors talk to the boundary objects. There are these data structures that we use to pass in and out. Controllers control the input. Presenters deal with the output. We still have controllers. We still have views. We still have a model view controller architecture, but it's back more towards the way Reenskog would have had it. What about the database? Anybody got one of those? A system with the database in the middle, and the database is boldface, and the rest of the system is tiny little things. This is the way you think about it. Do you think about your system this way? I would ask you not to. The database is not the center of your application. The database is a detail. We don't like to think about it that way. We have been taught for years that databases are the most important part of the system. You have to get your data model right early. You have to know what the data structures are going to be. The database is at the center of everything. No, database is a bunch of bits. The database is where you store bits. And there are nice little facilities that it gives you to access those bits. But the database is not where the business rules are. Anybody got a bunch of business rules and stored procedures? Not anymore.
Yes, of course.
A lot of people do.
Yes, but if you have to support several database systems,
Yep,
it can serve as an abstraction layer.
definitely can.
Yes, depends how deep you nested it, but
Definitely can. Is that stored procedure part of the database? Or is it just another programming language?
it's another layer.
It's another layer, another programming language. Does it need to be part of the database? Is there anything that forces that to be part of the database? Some things do. For example, if you want to do data integrity checks, it's really handy if it's the database that does that, or really close to it. If you want to do back pointer checks, back reference checks, there are certain triggers that you'd like to have. Generally, those have nothing to do with business rules. Usually those are technical things, wiring for the data. And stored procedures in the database are a great place to do that. The business rules, on the other hand, you would not like to have in the database or controlled by the database processor. You'd like to somehow get those out of the database, because it's not a database job to do business rules. Could you have another layer of abstraction that gives you some kind of portability? Sure. And a good database system will allow stored procedures to behave that way. Myself, I don't like using them. I would prefer not to use stored procedures except for data integrity issues and query optimizations. Other than that, I'm not going to put any kind of business rules into stored procedures. I once saw a database system, a system that had a stored procedure that scanned through a bunch of user records, generated emails, and sent the emails to all the users. This is not a good use of a stored procedure. Stored procedure should not be doing mail merge. There are better languages for that. The database, from the point of view of the application, is a detail. We don't want to know that it's a relational database we're using. Why do the business rules care? They don't. We don't want the business rules to know about SQL. Why should they care about that? They shouldn't have to. SQL is something that you use at a lower level. So I want to put in another boundary. Got this black line here. Another boundary. Here's our interactor. Our interactor uses entities. It is the entities that we usually think of as being in the database. But they're not. They're objects. And as we talked about before, objects are piles of methods, not piles of data. They may have data in them, but that data is hidden and in a form that you're not allowed to see. The data that is in the entities certainly must reside in the database, but the form of that data can be radically different. Most people will create tables down here, and then they will create objects for each table. Anybody using Hibernate? Okay, lovely tool. I love the tool. It belongs down here, below the line. I don't want any Hibernate stuff up here. Right? Hibernate lives down here because what Hibernate is good at is taking data out of the database and putting it into data structures that can then be passed across that line. Lots of times what you'll do is you'll pull data from this table, data from that table, data from this table, essentially doing a join. You'll load it into an entity structure, and then you'll pass that entity across the line. Every application may have a different set of entities, or a different way of constructing those entities. Nothing up here knows that this exists. The interactors are the ones that know that entities need to be read and written. They're the ones that control transactions. Interactors are the ones that have the application-specific business rules, so they know about transactions. They talk to an interface, a Java interface or a .NET interface, and the methods here are methods for every database operation, every insert, every update, every query. Every kind of query is another method in the gateway. You probably have many of these interfaces. Those interfaces are implemented below the black line by some kind of gateway or database repository or something which then controls the database. And once again, notice the direction of the arrows. The arrows point inwards across the black line. The database is a plug-in to the application. The database can be put into a jar file or a DLL and shipped independently of the application. You can test the application without the database by stubbing this out. Right down there, another jar file with stubbed data. Just stub it all out. I'll tell you the story of fitness, how it started. It was about 2002. I was at a conference in Minneapolis. It was the OOPSLA conference. Anybody been to an OOPSLA? Nobody goes to them anymore, so don't worry about it. But back in the day, OOPSLA was the primo object-oriented conference to go to. If anybody was anybody, went to OOPSLA. And I was at OOPSLA in 2002, and I bumped into Ward Cunningham. And I told you who Ward Cunningham was, the inventor of the wiki. And Ward said, Bob, come here, look at this. And the two of us found some stairs, and we sat down on the stairs, and he flipped open his laptop, and on his laptop was an image of the HP 35 calculator user card. Anybody remember those old HP calculators? Yeah. Did you have one? 35 or a 45? Or... Yeah. So these are the Hewlett-Packard calculators. These are like the first handheld multifunction calculators. They cost $350 when they first came out. Everybody had to have one. They were built like bricks. You could throw them against the wall and keep on working. Reverse Polish notation, right? They came with a little card. They came with a little card, and the little card was the user guide. It showed you how to use it. So on his screen was the HP 35 user card. I recognized it immediately. I said, that's the HP 35 user card. He says, yes, it is. Now watch this. He pushed a button on his laptop, and all the little elements of the card turned green. He had invented something that he called FIT. And FIT was a tool that allowed you to take an HTML table, unpack it, send it into an application, get the results back, and turn the table green if the tests pass. He showed me an HG35 user card written in that script, in that style, and showed it to me turning green because he had an HP35 simulator on his laptop. And I said, Ward, that's the user guide. You've turned it into a test. He said, yes, this is called FIT. I said, it's cool. How do you do it? Oh, you write HTML. I said, you're going to get people to write HTML? Yeah, because they can do it in Microsoft Word. And it occurred to me, Ward, you invented something else. It's called a wiki. It translates things into HTML. Let's do this in a wiki. And I said, I'll write this. So I went home and I got a bunch of my guys and we started writing Fitness. Fitness is a wiki. It translates wiki text into HTML for the purpose of loading it into Ward's tool called FIT. Or good enough for the moment. We thought about it for a while. We started with a design session, as you always do, even in an agile environment. Sat down, started designing things. Thought, well, okay, what are we going to need? Well, we're going to need this, that. We're going to need a database. Got to store those pages somewhere. Got to have a database. What database should it be? Well, we don't want to use Oracle. Don't want to pay for the license. Got to be open source. We need an open source database. What could it be? Well, there's only one. Back in 2002, MySQL. Okay, MySQL. Okay, what's the data model? Let's draw an ER diagram. And one of us said, wait, we don't need to do that yet, because we have this other problem. We need to translate wiki text into HTML. That has nothing to do with with the data model. And we kind of looked at each other and said, yeah, you're right. So for about 3 months, we did nothing but translate wiki text into HTML. This forced us to have a design. One of our objects was called wiki page. It had a whole bunch of methods on it. One of those methods was toHTML. That's the one we were writing. It had a save method on it too, because you need to call that from time to time, but it was overridden by a mock wiki page, which didn't do anything. For about 3 months, we wrote this code, making something that could translate wiki text into HTML. All the tests were passing. Couldn't see anything on the screen, but we didn't care about that. Just all the tests were passing, which was nice. After that, we got all the translation done. We said, okay, now we need that ER diagram. So let's sit down. We're going to do the data model for the database because we got to get MySQL running. And somebody said, well, wait. We don't really have to do that yet because all we really need to do is create a hash table of wiki pages so that we can have, a few wiki pages to access. And we can kind of hide the fact that there's no database by using a hash table. And we thought, that's not a bad idea. After all we're doing is writing tests. So we made this thing called in-memory page. And we put in the wiki page, we put all the methods to access the wiki pages. All the query methods would go up here. And then in-memory page would just use a hash table. And worked great. And for a year, we kept on developing fitness with nothing but that. We actually got the entire wiki working, displaying pages, running tests, all that stuff, without any persistence, which was very frustrating because we couldn't save anything. As soon as you tore it down, it was all gone. But that was all right because we were only writing tests. About a year in, we started to need to write some tests that depended on real persistence, boot up tests. You boot the system, it looks in some pages that have to be out on disk, and we wanted that to be real. So we said, all right, it's time to do the real database. And Michael Feathers was there at the time. And Michael said, well, you don't really need to do that because you could just take that hash table and write it out to the file system. That's a temporary measure, but it'll help you get these tests to pass. I said, yeah, that's true. So he actually came back a day later with this file system page written, and we kept on making progress after that. And now we had real persistence. It was file system, so it didn't have query optimization, it didn't have indexes, it wasn't fast, but it was good enough for our testing. And we found we could use the system for demonstration purposes. We could show it to customers. We could show it to students. We could actually use it in small projects. We kept on adding more and more to the software, more and more test cases, more and more pilot deployments. About 3 months later, we looked at each other and said, this is good enough. We don't need any database at all. We never did put it in. Somebody else did. One of our customers came along and said, we got to have this data in a database. Well, we said, why? File system seems to be good enough. And he said, no, corporate policy. All data assets must be in the database. It's the only safe place to protect data assets. Anyway, so we showed him that structure. And we said, look, what you can do is create a derivative here, call it MySQL page. He came back a day later with MySQL page. The whole thing was running in MySQL. It took him a day to do this, right? The whole thing was running in MySQL. We used to ship that as a plugin to Fitness, but nobody used it, so we stopped. He doesn't use it anymore either. He changed jobs. There's a lesson here. What we did in the development of Fitness was to take a fundamental decision, a fundamental architectural decision, and defer it. We intended to make it the entire time. This whole almost 2 years, we intended to make that decision. But we kept on deferring it, kept on putting it off. And in the end, we put it so far off, it fell off the end of the product. We never implemented it really, except for that one dumb customer. We shoved that decision off the end of the planet. A good architecture is an architecture that allows critical decisions to be deferred. Why? Because the longer you can defer them, the more information you have to make them. Sometimes that information says, you don't need it. Other times not. The more you can delay a decision, the more likely you are to make it correctly. We have thought about architecture in a different way in the past. We have thought, well, the way to get your architecture written is to make all these decisions. So architecture of our system is going to be Java, Swing, Oracle, Model View Controller. Okay. That's not an architecture. That's a bunch of tools. That's a bunch of frameworks and tools. It's not an architecture. An architecture is the structure of the system that allows you to not make those decisions. A plug-in architecture that allows you to say, well, the database decision can be made down here, and it's irrelevant to the application. The web decision can be made over here, and it's irrelevant to the application. And the web will be a plug-in to the application, and the database will be a plug-in to the application, and the credit service will be a plug-in to the application, and all these external services will be plug-ins to the application. The business rules will know nothing of them. All the arrows will point inwards, not outwards. A good architecture maximizes the number of decisions not made. Oddly, when you do that, your systems are much easier to test because you don't have the dependencies on these things that you have now deferred. Oh, we're going to defer the GUI. We're going to defer the database. In order to do that, you must create a structure that doesn't depend on them, and so you wind up with something much easier to test, much faster to test. Does this mean, if you're going to defer the GUI, does that mean that you don't implement the GUI right away? Are you just going to be spending all your time writing business rules and then finally at the end do the GUI? No one would ever let you do that. Because the business people all want to see the GUI working. Right? So, they don't care about the business rules. They don't want to see a bunch of fitness tests running. They want to see stuff on the screen. And no matter how much you tell them, it's irrelevant. They don't care. They want to see it on the screen. So fine, put it on the screen. Go right ahead, do the GUI development at the same time you do the business rule development, but maintain that boundary. Keep those arrows pointing in the same direction. Make sure that the GUI is always a plug-in to the business rules. Sprint number 1 can be a little tiny bit of GUI and a little tiny bit of business rules with all those arrows pointing in the right direction. A tiny bit of database coming up from the bottom. All of that stuff can be preserved. You don't have to do it all together. It is a plug-in model. And that plug-in model, like any plug-in model, is a set of components, DLLs, jar files, that have dependencies that point at the application. And the application does not depend on them. Looking at that diagram, it's very clear that these are plugins. Because they have ingoing dependencies, not outgoing dependencies. What's object-oriented design? Ponder that. And after the break, we'll talk about it. And something else. I'm not sure what yet. Fusion. Take a break.